Tyler. Let me stop this back.
Okay. Hello, everyone. Welcome to the final presentation for Team 2 of the Tasmaniacs. My team consists of Brooks, Ramel, Jonathan, Eliza, and myself, Tyler. On the agenda today, we have understanding the problem, what solutions exist, our personal solution and metrics, and what we've learned together as a team throughout the semester. Starting at the problem. We were tasked with designing an automated system that completes physical tasks and earns a maximum number of points in the designated amount of time. These tasks included jump shot, pass, collect, and dunk. The course setup can be seen on the right. The jump shot and pass must each reach 4 feet from our starting zone, and then our robot must move to the right to collect balls off of PVC pipes at varying distances and heights. Finally, the robot must move to the target zone and deposit the ping pong balls in a high-scoring zone. At the beginning of this project, we as a team defined our customer needs and assigned importance values to each of them. To the left, we have our original ratings. I have highlighted 3 needs here that I believe we underestimated in importance, and this became evident later on in the course when we began struggling in, say, the dunk task. If we can go back in time with the knowledge we have today, our HOQ would have been based more on the values on the right. This shows more prioritization of all crucial tasks as number 1 priorities. Moving on in the HOQ, we identified the key engineering requirements as power limitations, adjustability, precision, and accuracy. It was clear that sticking to our original power sources was vital as to not get disqualified, while adjustability was important to promote easy design iteration down the road. Requirements for precision and accuracy were needed to ensure a certain standard of quality for our robot's performance. On the next slide, you can see our breakdown of all the sub-functions needed to accomplish the given task. This includes jump shot aiming, ball collection, and moving the robot. The big change we made here compared to our original function tree is the separation of the pass and jump shot function. This was due to the rule clarification that the pass must hit the outside of the bucket. The next 5 slides show our original design choices before this rule change for historical accuracy. Getting into these is our first proposed design solution. This had a mousetrap jump shot and an actuator-driven platform on drawer slides that would collect the balls and release them over the cups via trapdoor. We saw this as not ideal due to the safety risk to the user and robot associated with the actuator ejecting the platform forward unexpectedly or too strongly. For our second proposed solution, we had an actuator-driven jump shot and a funnel collection system with a motor tilt to deposit into the cups. We moved away from this design because we didn't think that the funnel would reliably collect the balls by simply ramming into the PVC pipes. For our third solution, we once again had a mousetrap jump shot and a collection mechanism that would collect balls and place them into a funnel that would go right down onto a mousetrap so they would be ready to be launched. This design flaw was that it was complicated in nature and the team had a perception that the mousetraps were not precise enough sources of power to accomplish our task. For the fourth design solution, once again a pneumatic jump shot system was used, and a collection mechanism where balls would fall into a conveyor system, elevate, and then be released down a ramp into the cups was used. This was bad because it was more complicated and underperformed in the primary categories of dunking, passing, and free throws. Ultimately, this brought us to our initial preferred alternative. We settled on this design, and it uses pneumatics to launch both the jump shot and dunk towards their respective targets. Ball collection is done by a sweeper in the front, leading the balls to fall into our machine, then being elevated by conveyor to our pneumatic launch zone. While the evaluation matrix on the right makes this design look ideal, we ultimately pivoted from this design, realizing we had overestimated its feasibility. The most pronounced issues we encountered included its complexity in collecting the ping pong balls and the minimal accuracy regarding the dunk shot. Learning from this, our team was able to iterate our design to what it is today, and Ramel can go into more detail on this.
So our final design was called Taz, and we feel this name captures the craziness that was 2110. On the left, you'll see a picture of Taz in real life, and on the right, you'll see a CAD model of Taz, where you can see its subsystems, which I will further break down now. So first up is our jump shot system, which, much like our initial preferred design alternative, is a pneumatic system that launches the ball out of its resting position in the barrel via the pneumatic actuator. This is done at an angle and ideally hits the middle of the backboard and bangs right into the target zone. Next is the pass shot system, which features a solenoid release gate which retracts when an electric signal is applied, releasing the stock item down the ramp towards the target zone. Next up is our propulsion system, which features a direct drive system, which has the drive axle connected directly to the motor and also connected to the frame of the robot for stability reasons. The wheels are made of MDF and glued together to increase the wheel width to improve our traction. Additionally, rubber bands are wrapped around the perimeter of the wheel to also improve our traction. Finally is our dunk shot system. This system is dropped down through the release of a solenoid. We then collect stock items on the track as the PVC slides through the grooves in the fork. Finally, when we have approached the target zone, we lower the fork through use of a pulley system and hinges located on the fork, which then lowers the balls into the target zone, effectively dunking. Up next, you'll see videos of a sample performance of our robot. On the left, you'll see the functioning of our jump shot and our pass system. On the right, you'll see how our collection mechanism and our dunk works. Altogether, we think this is pretty cool. So the question is now, why did we choose Taz over our original design? Well, there are two main reasons. The first is Taz's ability to retrieve ping pong balls. Taz's fork design is extremely effective at retrieving the balls. As Tyler noted earlier, we neglected the importance of this task, and Taz's fork provided a much needed improvement and simplification over our initial system's conveyor belt and sweeper. The next reason is reliability. Taz's modifications to barrel length and launch angle for a jump shot, improved traction for powertrain, and new fork design provided us with a system that performed much more reliably than our initial design. And this leads us to discuss our machine's performance. On the screen are several statistics of how our machine performed. The first statistic I'll note is the pass success rate, which is almost 100%, or I should correct myself, was actually 100%. The next is the jump shot rate and the dunk and orange rate, which are both 87.5%. What this doesn't represent, however, is that as our operators gain more experience continuously running trials, our alignment of the robot improved. Our robot became even more consistent, scoring near its maximum points each trial. This all culminated in our robot earning 22 points or more in each trial for the final performance. So what did we cover today? First, we redigested our problem, which was to design an automated system that completes physical tasks and earns a maximum number of points in the designated time. Next, we discussed our design alternatives and broke down our final design. Finally, we discussed our machine's performance. Now, over the course of this semester, we learned several things. The first is that requirements must be fluid. Rule changes, new information, and experience led our team to prioritize different things as the semester progressed, which needed to be reflected in our robot. Next is that traction is extremely important. Traction failures could lead to the failure of a robot if it depends on wheels as its main primary method of transportation. The next is that modularity and iteration are key to improvement. And these two principles allowed us to iterate upon our design and improve parts of our robot without requiring a complete redesign and rebuild, which allowed us to keep testing and keep improving our robot, ultimately resulting in its success. This concludes our presentation, and thank you for listening today. We'd be happy to answer any questions that you might have.